Bam! Mr. Tarrou. In this math lesson, we are going to be taking a look at some numerical integration problems in the form of estimating definite integrals using the trapezoidal rule and Simpson's rule. And in our lesson, we're going to work out this example you already see on the board. And notice I haven't given you any notes yet. We're going to work out this problem just understanding how to find the area of a trapezoid. And we're going to find the area of 4 trapezoids. After you see this example sort of worked out with just our knowledge of, a little bit of knowledge of what definite integrals are finding and just, the area of a trapezoidal formula, I'm going to write out that example and then somewhere put a line in that work that lets you see the tie-in with just your basic geometry skills and knowledge and what you'll see in my green picture-in-picture of what the trapezoidal rule actually is or says, and tie those together to kind of show you that you can do these problems even if you don't remember exactly what the trapezoidal rule says. Now, in calculus, we don't want to, not memorize the formulas and theorems and derivative and integration formulas through the process of going through this class. It's actually very important, but just to show you how to work out this problem using skills you already know. We're going to then discuss when trapezoidal rule is going to over or underestimate the definite integral. We're going to do another example, which you might see on a standardized test or later on in the problems in your textbook, where we're going to not know what the function is. We're just going to have a table of values, kind of like a t-table, and use the trapezoidal rule to estimate the definite integral based off the information in that table. We're then going to talk a little bit about Simpson's rule. I'm going to give you a diagram to explain exactly what's sort of happening there, give you the Simpson's rule, and then work through this problem again, estimating. We're going to estimate this definite integral using the trapezoidal rule and Simpson's rule. I'm not going to derive the Simpson's rule. You can look at your textbook for that. It's quite a complicated derivation. And in our next lesson, we are going to be calculating the maximum possible error that we can get from these rules based on a certain number of intervals that we're going to set n equal to. So in this case, we're going to estimate the definite integral using 4 trapezoids. Okay. Really, before I get started, the real power of the trapezoidal rule and the Simpson's rule for estimating definite integrals is so that you can work out problems that maybe you couldn't otherwise, work out. Let's take a second and actually forget the fact that we're going to estimate this definite integral of 4 trapezoids and just calculate this definite integral. We have the definite integral from 1 to 3 of x cubed dx. Well, this is a very basic elementary function. And to integrate this using the power rule, we're just going to raise that power by 1 and then divide. So we're going to have the definite integral from 1 to 3 of x cubed dx is going to become, raising that power by 1, we're going to have x to the 4th. And then, dividing by that raised power, we're going to divide by 4 and multiply by 1/4. And that's going to be from the values of 3 and 1. Now, working this out, we're just going to have, 1/4 of 3 to the 4th power minus 1/4 times 1 to the 4th power. Well, 3 to the 4th power is 3, 9, 27, 81. So we have 81 over 4 minus 1/4. Nice, we already have common denominators. And with those common denominators, we subtract the numerator and get that it's equal to 81 minus 1, which is 80, over 4, which is 20. So the definite integral from 1 to 3 of x cubed dx is equal to 20. And because the function is above the x-axis through that entire interval from 1 to 3, you can possibly say that that might be an application problem dealing with area. And of course, definite integrals are not just giving you areas, it's a limit of sums. So why bother with this idea of estimating definite integrals using the trapezoidal rule and Simpson's rule? Well, it's not very hard for me to come up with a function like, let's estimate from 1 to 3 the square root of, I don't know, how about 4 minus, since we already use x cubed, 4 minus 5x cubed dx. We do not have any way of calculating that definite integral. We can't integrate this, not with any elementary techniques that we have. So the problem is, we have an inside function in the square root, here. Now, if maybe I change this problem with just a little bit and say we have the definite integral from 1 to 3 of maybe 2x squared times the square root of 4 minus 5x cubed dx, and depending on where you are in your calculus studies, you can do a little bit of u substitution to rewrite this expression into a form that will integrate, but this one will not. So if you want to calculate the definite integral from 1 to 3 of the square root of 4 minus 5x cubed, well, unless you're just going to be completely reliant on your calculator, you're going to want to do that with the trapezoidal rule or Simpson's rule. Okay, so that is the power right here, especially this example. That's the power of the trapezoidal rule and Simpson's rule. Now, if you're in a class that allows you to use a calculator, then maybe this technique is a bit, I don't know, outdated or not something that you would go to immediately. But if you're in a class or studying this and you really want to actually know how to estimate these definite integrals, let's do it in a nice way using this trapezoidal rule or Simpson's rule. Now, we already understand when we develop the idea of definite integrals, we've already estimated areas using rectangles when we talked about lower sums and upper sums and estimating areas using midpoints. But the problem with that, you see, is if I want to, say, find the lower sum or estimate the area, this area between the x-axis and the function y equals x cubed from 1 to 3, if I talk about a lower sum and I just do that with 4 rectangles, you can see how much these 4 rectangles, how poorly it's going to estimate that definite integral, because you're going to underestimate by quite a bit. But if I just use 4 trapezoids, look how closely these particular legs of these trapezoids follow the curve. So even with just 4 trapezoids, we're going to have an estimation that's pretty close. Now, how are we going to do that? Because again, I didn't give you the rule. Well, how do you find the area of a trapezoid? The area of a trapezoid from geometry is 1/2 the height times base 1 plus base 2. So, or in other words, it's the height times the average of the 2 bases, the height of the trapezoids. Well, because we are going to find the definite integral, estimate the definite integral from 1 to 3, that's 2 units along the number line. So we're going to do 3 minus 1, of course, we just said, is 2. And we're going to take that length of 2 and divide it into 4 subintervals, in this case, all even. And so we're looking at trapezoids that all have a height of 1/2. So far we're looking at the area is equal to 1/2 the height times base 1 plus base of 2. Well, of course, maybe the heights of each of these trapezoids are all a value or length of 1/2, but as we go through this interval, obviously the lengths of these bases are going to be changing, and they'll be based on the value that you're getting from the function itself. So how long is this base? Well, the y value that you get from the function when you plug in 1 is 1, and 1 minus 0 is a length of 1. And the length of this base here is going to be, well, we're going to take the value of 1.5, plug it into the function, and 1.5 or 3/2 cubed comes out to a value of 27/8. And again, if we, or just not again, but if we take the value of 2 and plug it into x cubed, we have 8. If we take the value of 2.5 or 5/2 and cube that, because that's what the function is, we're going to get 125/8. And then finally we have the last point of 327. So I've already set up this diagram because I didn't want to freehand that in front of you and make it a little bit sloppy and take up some time, but I'm letting the value of the function x cubed, y equals x cubed, those values be determined, those lengths of those bases be determined by that function. And with all that information into the table, we can just say, okay, I want to estimate this definite integral of 4 trapezoids. Well, then the area of these trapezoids added together, and really this definite integral again is going to, can be an area because the function is above the x-axis, giving us all those positive values, those positive sums that we are adding. So the area, or let's say this, the definite integral from 1 to 3 of x cubed dx is approximately equal to 1/2 times the height of these trapezoids times the first base. So that first base, it doesn't matter how you do this, but because it's addition is commutative, but I'm just going to go left to right. That base right there is equal from 0 to 1 is a length of 1, plus our second base right here. So I'm looking at our first trapezoid, and that base is going to be 27/8. And that is the area of that first trapezoid. Hopefully you're seeing that the bases are vertical and kind of like need to turn your head sideways to sort of see the orientation of those trapezoids, like you probably would have seen in your geometry book where the bases were horizontal. And then we have another 1/2 because we're doing 1/2 the height. So the height again of those trapezoids are 1/2. Now moving on to the next trapezoid right here, we have a base which is 27/8 and another base which is 8. I'm going to step off and reveal the work one step at a time to make it a little bit neater, but whenever I have problems that have fractions in them, I tend to just write everything so that it looks like a fraction. Plus 1/2 times 1/2. Our next trapezoid is going to be has a base of 8 and another parallel base of 125/8. And then finally our fourth trapezoid is got again a height of 1/2 and a base of 125/8 and 27. So we can see that all I'm doing is using the area of a trapezoid formula 4 times, and we can also see just by drawing how much better the estimation is going to be of this definite integral using those 4 orange trapezoids, as opposed to the idea of using just simply 4 rectangles where the left endpoint of those rectangles is determined by the function. And instead of having an estimation of this definite integral, which is going to be very, very, very underestimated or overestimated if I use the right endpoints, at least from the drawing, it looks like we're going to be pretty close. So there you go. I did change the notation a little bit to match the notation that you're going to see in the trapezoid rule here in a second. I went back and showed where those values, where the 1, the 27/8, 8, and so on, where those values came from, and used the function notation. We have 1/2 times 1/2 of, again, where's your base 1 and base 2 coming from? 1/2 times 1/2, base 1, base 2, and so on and so on. And worked through the notation. I wouldn't do this if I was just, doing one problem with trapezoidal rule and I didn't know the rule. But I want to show you with an example sort of where the rule comes from. We took from each of these, or all 4 of these terms, all 4 of these terms have a common factor of 1/2 times 1/2, so we're pulling that out. Then we see that we have f of 1, f of 3/2, again another f of 3/2, and a couple of f2s, a couple of f of 5/2, and finally our f of 3, the last function, or the last value, the upper limit of our definite integral getting plugged into our function. Well, when you factor the 1/2 times 1/2 out of each of these 4 terms, you see that, yeah, there's a couple of, there's some like terms that you can add together. So there's 2 f of 3/2 and 2 f of 2s and so on. I know you can read that. And now I'm stopping and I'm saying, okay, remember it was 1/2 times the height times the sum of our 2 bases. So, well, where did the 1/2 come from? Where did the height come from for each of those trapezoids? The height of that 1/2 came from doing the upper limit of the definite integral minus the lower limit of the definite integral divided by how many trapezoids you wanted to use to estimate that definite integral. So I'm just showing, again, this is only for the purpose of showing how this arithmetic and our past knowledge of just basic geometry ties in with the trapezoidal rule. So I'm writing that 1/2 as I calculated it, 3 minus 1 over 4. And then finally just continuing to, okay, let's take the function out and remember that the function is simply x cubed, so 1 cubed. I maybe should have put a 3 on that just for academic purposes. And then we're taking the value of 3/2 and plugging it into, again, the function x cubed and the next value of x cubed and so on and so on. Now, putting those actual y values back into the problem that I had in our discussion, 3/2 cubed is the 27 over 8, 2 cubed is 8, 5/2 cubed is 125 over 8, and we come out to 20.5. Now remember, because this is a definite integral that we could evaluate using our skills that we've learned so far in evaluating definite integrals, we know the answer is really 20, and with just only four trapezoids, we got an estimate that was really quite close. It's 20.5, so you can see the power of this trapezoidal rule, how close the estimation is of that definite integral, even with only 4 trapezoids. And if you made 5 or 6 or 7 trapezoids instead of just 4, you would get an estimate quite close. And we'll talk about that expected maximum error in our next lesson. Now, I did a lot of explaining just to tie your own knowledge in with your new knowledge, but you can see here this line where I particularly said I want to tie all this old school arithmetic and basic geometry knowledge with our trapezoidal rule and focus down on here. If you know the trapezoidal rule, you would have just picked the problem up here and finished, and you can see it's not very much work either. So this, getting our fancy picture-in-picture, is what the trapezoidal rule says. The trapezoidal rule, let me get the glare out of here from the window, if there is any. Let f be a continuous function on the closed interval from a to b, and if that condition is met, we have the definite integral from a to b of f of x dx is approximately equal to b minus a over 2n times f of x sub 0 plus 2 times f of x sub 1. This x sub 0, as you saw through our arithmetic, is simply that initial x value. That x sub 0 is going to be your a value, the lower limit of your definite integral. And then just working through those steps as you saw me doing with my 1 and 3/2 and 2 and so on. And I again stepped through those x values through the calculation of b minus a over, well, I just did b minus a over n, so it's a little bit curious, where's this 2n coming from? I'll talk about that in a second. And so you plug in your x sub 0, x sub 1, x sub 2, and you start off with 1 times f of 0, 2 plus 2 times x, f of x plus, plus 2 times f of x sub 1, plus 2 times f of x plus sub 2, plus, and then you just continue that process, stepping through your interval along the x-axis, or just, well, you can find integrals, definite integrals along the y-axis as well. But so you just step through that interval of which you're calculating the definite integral until you get up to x sub n. Now that's going to be the upper limit of your definite integral. As n approaches infinity, as the number of trapezoids you're using to estimate the definite integral get larger and larger and larger, then the right-hand side of this rule is going to approach the actual definite integral and become a more, accurate estimate, as we saw with our limits, infinite limits of sums, and developing our idea of the first fundamental theorem of calculus and estimating area with rectangles. We let the number of those rectangles approach infinity, and whether we use the left endpoint or the right endpoint or the midpoint, we got an infinitely accurate estimate. Okay, the only thing bothering me a little bit here is this idea of b minus a over 2n, because you saw in my we're going to do this problem without actually knowing the trapezoidal rule. I did b minus a over n to calculate the height of each of those trapezoids. Well, yeah, the area of a trapezoid is 1/2 times the height times b sub 1 plus b sub 2. Well, if b minus a over n is the height, and we're estimating these areas with trapezoids, well, there's that 1/2 that's always going to be sitting out front, and that's where the 2n came from in the denominator of the trapezoidal rule. Now, which, just in case you want to see it again, voila! I knew before even starting that this estimation, I didn't maybe necessarily know how close the estimation was going to be to the actual answer of 20, but I knew that the estimate that I got from this trapezoidal rule, this particular example, was going to be a little bit of an overestimate. So let's talk about that right now. Bam! So we have functions which are increasing concave up, increasing but concave down, decreasing and concave down, and then we have increasing and concave up. As you look across these boards, across this board, what did you see in similarity with all of these answers? When did the trapezoidal rule overestimate it? Well, it overestimated when it was increasing, but it also underestimated when the function was increasing. But when the function was concave up and you connect 2 points along that function with a straight line, you're going to have, when the function is concave up, that trapezoidal rule is going to be overestimating your definite integral. And when your function is concave down, whether it's increasing or decreasing, when you connect those any 2 points along that function with a straight line, which would be effectively at one of the legs of that trapezoid, you're going to see it's going to fall a little bit below that function and underestimate the definite integral. So trapezoidal rule overestimates when your function is concave up, or the second derivative is positive, and it's going to underestimate when your function is concave down and your second derivative is negative. Now, if they just give you sort of a t-table or a table of values that represents a function, and you don't know the function, what the function actually is, what does that look like when you want to estimate the definite integral using a trapezoid rule? It's actually pretty simple as long as you know the rule. Alrighty then. For our last example dealing with the trapezoidal rule, we're going to use this table of values created by some function f of x. We have the x values of 1 through 5, and these given values coming from our function, and we want to estimate the definite integral from 1 to 5 of f of x dx using the trapezoidal rule with n equals 4. Now, why are they asking us to use 4 trapezoids to estimate the definite integral, which is defined by this function? Well, the x values of 1 and 2 are going to give us some y values, setting up 2 bases of our first trapezoid, and then 2 more bases of our second trapezoid, and then 3, and then our fourth adjacent trapezoid, going from that definite integral, or in this case along the x-axis, from 1 to 5. And unlike before, where we just did this using our area formula of a trapezoid from geometry, we have the trapezoidal rule now, and that'll speed up the process and allow us to do quite a bit less work. And the definite integral is approximated by, b minus a over 2n. So we're going to have the definite integral from 1 to 5 of f of x dx is approximately equal to b minus a. Well, that's going to be b minus a, so 5 minus 1, over 2n, and we explained where the 2 came from in that denominator in our previous scene. So 2 times n, 2 times the number of trapezoids you're going to use to estimate the definite integral. So that's going to be 2 times 4. And let's see, what else does it now say? Times, now we're going to take f of x sub 0, the function, the y value you're getting from the function using the very first x value in your definite integral, that lower interval. So it's going to be f of 1. Well, f of 1 is 2.236 plus, referring to our rule here to let you see how to read it, 2 times f of x sub 1. That's just simply the next number along the interval, next x or y value, if you're integrating along the y-axis, that's within your interval. So we're counting by, well, ones, obviously. And so f of x sub 1, or x sub 1 in terms of that notation, is going to be your 2. So we're looking at 2 times f of 2. Well, f of 2 is 3.17, and we're going to just keep with that idea of having a coefficient of 2 in front of the y value that we're getting in, from our function until we get to the last term in this rule, or we go to work with that last rightmost side base, or length of the base, that trapezoid. So we have, again, where was I at? 2 times f of 2 plus 2 times f of 3 looks a little bit like a 1, plus 2 times f of 4 plus, and now again, hopefully you understood from my sort of example, working through that example with our geometry knowledge, and not this rule why this last term does not have a coefficient of 2 in front of it. So make sure as you get to our beginning, on the first and last x within our interval, you don't put a 2 in front of there, and we have 7.28. So let me just step off and reveal this work one step at a time, and then move on to estimating definite integrals using Simpson's rule. Bam! Simpson's rule. We're going to first, though, tie in with, point out some more information that was going on with the trapezoidal rule, estimating a definite integral of the trapezoidal rule. Within each subinterval, f is estimated by a first-degree polynomial, or a line. And we can see here, I maybe put a part of a possible cubic function, or a sine function, or cosine function. But at any rate, when you're using straight line segments to estimate the movement of a moving, curving function, sometimes that estimation is not going to be that great, and sometimes it'll be very, very nice. And we saw with our first example, with only 4 trapezoids, we got a definite integral, an estimation that was within a half of a unit. And with these subintervals being b minus a over n still. But there is this idea of Simpson's rule that is going to allow us to estimate the movement of function f a little bit more accurately. Actually, in some cases, a lot more accurately than we even can with trapezoidal rule, which is a lot of times, much better approximation than just using, of course, a finite number of rectangles. So we're just improving our estimation processes of these definite integrals. So the Simpson's rule, instead of using just linear functions to, or line segments, if you will, to estimate the movement of a function, I want to say polynomial, but it could be any kind of function really. With Simpson's rule, the subinterval are grouped into pairs. In each double subintervals, you can estimate f by a polynomial of degree of less than or equal to 2. 3 points may be collinear, but if not, a quadratic can be found passing through those 3 points. Now, here's where we come in the idea, getting down here through this reading, of why we have to have subintervals grouped into pairs. If we take our subintervals and we group them into pairs, which is going to be a problem for my diagram, by the way, because I've got 1, 2, 3, 4, 5 subintervals, which is great if you want to estimate a definite integral using trapezoids, but it's not going to work when you're going to estimate a definite integral with Simpson's rule, because you need to have an even number of subintervals. They need to be grouped into pairs, or into double subintervals. Why? Because within, like say here, we have a double subinterval, and we got 1, 2, 3 points coming from that function within that double subinterval. Well, that should sound familiar. We have before when, well, let's just read it. This should sound familiar when you studied three variable systems or matrices. Back when we learned about working with three equations and three unknowns, and working with Gaussian elimination method, and then moving into matrices, and maybe still doing Gaussian elimination with, with matrices, or you might have been doing Cramer's rule to solve those higher order polynomials. Not those higher order polynomials, but that's another technique. But those systems of equations that had, technically can work with two equations, but we have other techniques for that honestly is probably a little bit simpler, but when you're working with those three equations and three unknowns or more. But specifically three equations, three unknowns, you had problems that dealt with, hey, you have a parabola passing through these 3 points, find the equation of that parabola. And I've included those kind of problems in my lessons as well. I'll include one, a link to one in the description of this lesson. And you can see I'm trying to draw first a red and then a green parabola through these double subintervals and estimate the movement of my yellow function with those parabolas. And it's, hopefully you can see a little bit of variation, because I'm just trying to show you that Simpson's rule is not going to give you an exact approximation. But yeah, when you have a curving function and then you just take little pieces of that curving function and try to estimate its movement with a parabola, often that parabola is going to very closely track the movement of whatever other function is involved or within your definite integral. But my problem here is I've got a double interval here, so I've got my 1, 2, 3 points, my parabola, my quadratic's going to pass through. I have another double interval here, so my 1, 2, 3 points, but that last interval is a problem. See, if I went in, well, I'm going to, just for purposes of making it easy to draw this picture, we're going to have to change this problem. I don't want to try and draw, say, 6 points within this interval, but maybe I could extend the interval to include just one more point, and maybe something like this, where now I've got 1, 2, 3, 4, 5, 6 subintervals within this region along the x-axis, and now I can come through and maybe say that that parabola right there, that quadratic right there, is going to be used so that we have this double subinterval and that one quadratic estimating that part of the definite integral, and then we have this double subinterval and that green parabola being used to estimate the movement of my yellow function within this interval of, say, I don't know, maybe that's 2 to 4. And then finally finding my red chalk, we have our first parabola you saw me reveal in my beginning of this scene, where that red parabola is going to estimate the movement of my function between the value of 0 and maybe 2, if you will. Again, I didn't give you really a scale on the x-axis, but that's what's going on with Simpson's rule. But yet, the formula looks very similar to the trapezoidal rule. It just seems like some of the coefficients are changing, but you're estimating movement of a function with a parabola, possibly, instead of just being limited to estimating its movement with a line segment. Simpson's rule. Let f be a continuous function on the closed interval from a to b, and let n be an even integer, because, as we just showed you, it can't be odd. You need double subintervals. The definite integral from a to b of f of x dx is approximately equal to b minus a over n, not 2n like before, times f of x sub o plus, now instead of before, like where it was always just 2, it's going to be 4 times f of x sub 1, and then it's going to go back to 2. 2 times f of x sub 2, then go back to 4. 4 times f of x plus f of x sub 3. And now, again, your first coefficient's 1, and now it's going to start to flip-flop or cycle back and forth between 4, 2, 4, 2, 4, 2, and then as you get to the end of this sequence of notation you're going to write out, sequence of addition that you're going to write out, we have 4 times f of x sub n minus 1, and then that's going to be your last coefficient just before your last term, which has a coefficient of 1 again, plus f of x sub n. And just like before, as you let the number of subintervals increase to infinity, the right-hand side is going to approach the left-hand side, giving you, you know, we're not going to let n approach infinity in these problems, but it would approach giving you an infinitely accurate example if you use an infinite number of subintervals. But as you're going to see, with this particular example, I'm just going to redo again the problem I did at the beginning of this lesson. I wanted to give you a problem we could do with through the techniques of an understanding of the first fundamental theorem of calculus that we've learned up until now, and then show you a comparison with that same problem using the trapezoidal rule and now the Simpson's rule. Estimate the definite integral using Simpson's rule, and we're going to do again the definite integral from 1 to 3 of x cubed dx with n is equal to 4 using the Simpson's rule as opposed to trapezoid rule. So this is approximately equal to, just for purposes of space, I'm just going to say that's what we're going to do. It's approximately equal to, what do we have here? B minus a over n. So that's going to be 3 minus 1 over n, which again was going to be 4 subintervals. You'd have a problem if that was 5. We couldn't do it with the Simpson's rule, could with the trapezoidal rule, times f of x sub 1. So that's going to be, plugging in 1 here, we have times 1 cubed plus 4 times f of x sub 1. And remember our subintervals were 1/2, so we had 3/2 cubed plus 2 times moving another, that b minus a over n, that 3 minus 1 over 4, which was 1/2. So that's going to be 2 times 2 cubed plus 4 times 5/2 cubed. And that's our moving in here, we had 1, 2, 3, and then our fourth subinterval is going to be plus 3, losing my place here a little bit, cubed. Now, right off the top of my head, actually I already did my notes, but I know that after you do this arithmetic, this is going to come out to be approximately equal to 20. Now, in this particular case, using 4 subintervals with the Simpson's rule, remember we started this lesson off by doing this problem, with the first fundamental theorem of calculus, and we knew that the actual answer was going to be 20. In this case, the estimate that we got from Simpson's paradox, no, I'm not teaching statistics, Simpson's rule came out to be the same. So our estimation actually is exactly equal to the answer of 20. Now, it is an estimation though, so we're going to talk about in our next lesson how to calculate the maximum possible error or the maximum error to expect when using trapezoidal rule and the Simpson's rule to estimate definite integrals. They're not always going to be exactly the same, but as you can see, they can be the same. Actually, I'm sure with either one of these methods, well, more likely with Simpson's rule than the trapezoidal rule. But that is the end of my lesson. I'm Mr. True. Go do your homework.